A heroin addict sits alone, staring at the needle in trembling hands. They hate this drug. It stole their career, their family, their health. They're disgusted by what they're about to do. They know, with absolute clarity, that using will make everything worse. They don't even enjoy it anymore. The high disappeared years ago, and yet they want it. More than food, more than sleep, more than anything else in the world. They want what they despise. They crave what brings them no pleasure. How? How is this even possible? This isn't a moral failing. It's not weakness. It's neuroscience. A specific, measurable malfunction in one of the brain's most elegant systems. And understanding it will completely reshape everything you thought you knew about desire, motivation, and what it means to want something. Tonight, we're going to unravel one of the brain's most elegant paradoxes, a chemical system that was completely misunderstood for decades, that scientists insisted was about pleasure, when it was actually about something far stranger. We'll discover why your brain lies to you about what will make you happy, why some people can't stop pursuing things that bring them misery, and why understanding a molecule called dopamine might be the key to understanding what it means to be human. But here's the twist you won't see coming. Everything you've heard about dopamine is probably wrong. The feel-good chemical? Not quite. The reward molecule? Missing the point entirely. The truth is far more unsettling and far more beautiful. Take a slow breath. Let your mind settle into curiosity. Because this story begins with a scientist in Sweden who noticed something impossible happening in his laboratory. Something that would eventually win him a Nobel Prize and transform our understanding of the brain. And it starts with paralyzed rabbits that could suddenly move again. Part 1. The Mystery of Motion. The year is 1957. In a laboratory in Lund, Sweden, a young pharmacologist named Arvid Carlsson has just witnessed something that shouldn't be possible. He's been studying a drug called Rezapine, a medication used to sedate patients and lower blood pressure. When he gives Rezapine to rabbits, they become completely immobilized. Not sleeping, not unconscious, just frozen. Unable to initiate movement, as if some invisible conductor had dropped the baton mid-symphony. This in itself wasn't surprising. Rezapine's sedative effects were well known. But Carlsson noticed something the other researchers had missed. The rabbit's symptoms looked eerily familiar. The rigidity, the tremors, the inability to start voluntary movements. These weren't just sedated animals. They looked exactly like human patients with Parkinson's disease. Carlsson began measuring chemicals in the brains of these paralyzed rabbits, and he found something, a dramatic depletion of a substance called dopamine, concentrated in a region called the basal ganglia, an area known to control movement. Now here's where it gets interesting. At the time, dopamine was considered nothing more than a chemical stepping stone. Scientists thought it was just a precursor to noradrenaline, a known neurotransmitter. Dopamine itself? Just a middleman. Unimportant. A waypoint in a larger chemical journey. But Carlsson had a hunch. What if they were wrong? What if dopamine wasn't just a precursor? What if it was a neurotransmitter in its own right, with its own crucial functions? To test this, he tried something radical. He gave the paralyzed rabbits L-Dopa, the chemical that the body converts into dopamine. If dopamine really was just an unimportant middleman, this shouldn't do much. But if dopamine mattered on its own, the rabbits started moving again. Within hours, the paralysis reversed. The animals that had been frozen, trapped in their own bodies, were suddenly mobile, active, responsive. Carlsson had restored their dopamine, and with it, their ability to move. The scientific establishment resisted this finding. How could a mere precursor be so important? But Carlsson persisted. he developed increasingly sophisticated methods to measure dopamine in brain tissue using spectrophotofluorimetry that could detect minute quantities by measuring fluorescent properties. He mapped dopamine's distribution and found the highest concentrations in the basal ganglia, precisely where motor control is coordinated. And then came the connection that would change medicine forever. If dopamine depletion caused Parkinson's-like symptoms in rabbits, could Parkinson's disease in humans be caused by dopamine loss? Researchers began examining post-mortem brain tissue from Parkinson's patients. What they found was striking. Dopamine levels in the basal ganglia were reduced by more than 90%. The neurons that produce dopamine, located in a region called the substantia nigra, were dying, withering away, leaving patients trapped in progressively immobile bodies. This discovery opened an extraordinary door. In 1961, Walter Birkmeyer and Ole Hornikiewicz in Vienna gave L-DOPA to living Parkinson's patients. The results were promising but modest. Small improvements, temporary relief. But in 1967, George Kotzius at Brookhaven National Laboratory discovered that high doses could produce dramatic, sustained improvements. Patients who hadn't walked in years could suddenly stand. Hands that had been frozen could move again. Faces that had been mask-like could smile. L-DOPA became, and remains, the frontline treatment for Parkinson's disease. And for his discovery that dopamine functions as a neurotransmitter, Arvid Carlsson received the Nobel Prize in Physiology or Medicine in 2000, shared with Paul Greengard and Eric Kandel. But here's what nobody realized yet. Dopamine's role went far beyond movement. In fact, the paralysis story was just the beginning. Because while Carlsson was studying rabbits in Sweden, other researchers were making strange discoveries about reward, motivation, and something that would eventually be called addiction. And these discoveries would reveal that dopamine was involved in something much more complex than motor control. It was involved in desire itself. Part 2. The Rats Who Couldn't Stop. Let's step back to 1954, 3 years before Carlsson's breakthrough. Two researchers, James Olds and Peter Milner, were conducting experiments on rats. They'd implanted electrodes in the rats' brains and given them a lever. Press it, and a small electrical current would stimulate specific brain regions. The rats pressed the lever, and then they pressed it again, and again, and again. Not occasionally, not in moderation. Some rats pressed the lever thousands of times per hour, for hours on end. They would ignore food even when hungry. They would cross electrified grids, enduring painful shocks, just to reach the lever. They chose brain stimulation over eating, over sex, over sleep. Some rats, given unlimited access, would stimulate themselves to the point of physical exhaustion. This was the discovery of intracranial self-stimulation, proof that certain brain regions, when activated, produce experiences so powerfully reinforcing that animals will pursue them compulsively, even at great cost. The most sensitive areas for this effect turned out to be along the medial forebrain bundle, particularly regions rich in dopamine fibers. Over the next decades, research revealed a consistent pattern. Virtually all addictive drugs, cocaine, amphetamine, heroin, nicotine, alcohol, despite their diverse chemical structures, shared one property. They all increased dopamine levels in a specific brain region called the nucleus accumbens. This seemed to solve the puzzle. Dopamine must be the pleasure chemical, the feel-good molecule, the neural substrate of euphoria. When drugs flood the brain with dopamine, they create intense pleasure, which drives addiction. Simple, right? Except it's completely wrong. The first hint that something was off came in the late 1980s. Kent Berridge, a neuroscientist at the University of Michigan, was studying dopamine and reward. He decided to test the prevailing theory directly. If dopamine creates pleasure, then depleting dopamine should eliminate the ability to feel pleasure from rewards. So he did exactly that. Using pharmacological techniques, Berridge depleted more than 95% of dopamine in rats' brains. These rats, as expected, stopped eating on their own. They became profoundly unmotivated, aphagic and adipsic, unable to initiate feeding or drinking. Without intervention, they would starve. This seemed to confirm the theory. No dopamine, no reward, no motivation. But then Berridge did something clever. He directly measured the rats' pleasure responses, their hedonic reactions, to sweet tastes. Rats, like humans, have stereotyped facial expressions for different flavors. Positive reactions to sweetness, tongue protrusions, lip licking. Negative reactions to bitterness, gapes, head shakes. He placed sweet liquid directly into the mouths of these dopamine-depleted rats. And the rats liked it. Their facial expressions showed normal pleasure responses. They still found the sweetness pleasant. The hedonic experience was intact, but they wouldn't work for it. They wouldn't seek it out. They showed no motivation to obtain something they clearly enjoyed when it was given to them. Berridge then tried the opposite experiment. Using electrodes, he artificially increased dopamine activity in rats' brains. Did this make food taste better? Did it amplify pleasure? No. The rats' hedonic reactions to tastes remained unchanged. They didn't enjoy food more intensely, but they wanted it more. They worked harder for it. They approached food-related cues with greater vigor. They showed more intense motivation to obtain rewards, without any change in how much they liked those rewards when they got them. This was the bombshell that shattered decades of assumptions. Dopamine doesn't create pleasure. It creates wanting. Let me say that again, because it's crucial. The molecule that scientists called the pleasure chemical. For decades, the neurotransmitter everyone assumed mediated euphoria and happiness doesn't actually cause pleasure at all. It causes motivation. It creates desire. It generates the urge to pursue. But not the joy of obtaining. This discovery, published in a series of papers in the late 1980s and early 1990s, should have been front-page news. It fundamentally rewrote our understanding of motivation, reward, and desire. Yet it took years for the implications to fully permeate neuroscience and psychology. Part 3. The science of craving. The distinction between wanting and liking might seem subtle, even semantic. In everyday language, we use these words almost interchangeably. We want things we like. We like things we want. But in the brain, Berridge discovered, these are completely separate processes, mediated by different neural systems. Wanting, what Berridge termed incentive salience, is mediated by dopamine pathways, particularly the mesolimbic pathway projecting from the ventral tegmental area, VTA, to the nucleus accumbens. When dopamine is released in this circuit, it doesn't generate pleasure. It generates motivation. It makes cues associated with rewards attention grabbing, makes the pursuit of rewards feel urgent, creates what we experience as desire or craving. Liking, the actual hedonic pleasure of consumption, is mediated by entirely different systems involving tiny regions in the nucleus accumbens and ventral pallidum that respond to opioid and endocannabinoid signaling. Berridge called these hedonic hotspots, remarkably small areas, often just a cubic millimeter in size, where neural activation amplifies the pleasure response. These hotspots work in concert. When you stimulate opioid receptors in these specific regions, pleasure responses increase. When you block them, pleasure diminishes. But dopamine has little direct effect on these hotspots. Think about what this means. You can have intense wanting without much liking, and you can have liking without much wanting. Now remember that person we started with, sitting in a dim room, trembling hands reaching for something they hate. This is addiction. This is the wanting-liking dissociation taken to its tragic extreme. With repeated drug use, tolerance develops. The brain adapts to repeated dopamine surges by down-regulating receptors, reducing synthesis. Homeostatic adjustments attempting to maintain balance. The result? The same dose produces less pleasure. The drug doesn't feel as good as it once did. The liking diminishes, but simultaneously, a different process unfolds. Sensitization. The dopamine response to drug-related cues, the sight of paraphernalia, the presence of certain people, the smell of certain places, actually increases over time. These cues become supercharged with incentive salience. They grab attention compulsively. They trigger overwhelming craving. Based on decades of animal research and human neuroimaging studies, this sensitization appears remarkably persistent. In rodent studies, sensitized dopamine responses to drug cues can last months or even years after the last drug exposure. In humans, recovering addicts often report that even after long periods of abstinence, sometimes years, encountering drug-related cues can trigger powerful cravings. The incentive salience system has been durably altered, so you get this horrifying paradox: intense wanting without proportional liking. The person craves the drug, thinks about it obsessively, feels compelled to seek it out, yet derives less and less pleasure from using it. They want what they no longer like. Sometimes they want what they've come to actively despise, what causes them suffering, what they consciously wish they could stop pursuing. Berridge and Terry Robinson formalized this in what they called the incentive sensitization theory of addiction. The core idea: addiction results primarily from the progressive sensitization of wanting systems, not from the pursuit of pleasure. Dopamine pathways become hypersensitive, particularly to drug cues, creating a state of pathological motivation that can persist long after the drug itself stops feeling good. This explains why addiction is so hard to overcome. The problem isn't just that the drug feels good. In fact, it often doesn't anymore. The problem is that the wanting system has been rewired. Cues trigger craving automatically, non-consciously, through mechanisms that operate faster than deliberate thought or conscious intention. And it explains the paradox we opened with. Wanting and liking can come apart. And when they do, the results can be devastating. But here's the part that will really reshape how you think about dopamine. This separation isn't just about drugs. It's about everything. Every desire you've ever felt, every goal you've ever pursued, every time you've anticipated something intensely only to feel underwhelmed when you got it, every time you've worked incredibly hard for something that didn't bring the happiness you expected. That's the wanting-liking dissociation operating in normal life. And understanding it requires understanding what dopamine is really doing, which brings us to one of the most elegant discoveries in neuroscience. Part 4. The Brain's Prediction Machine. In the 1980s and 90s, while Berridge was discovering the wanting-liking distinction, another neuroscientist was making a discovery that would revolutionize our understanding of dopamine. Wolfram Schultz, working at the University of Freiburg in Switzerland, had developed methods to record the electrical activity of individual dopamine neurons in awake, behaving monkeys. He wanted to understand how these neurons respond during learning. His experiments were elegantly simple. A monkey sits in front of a screen. A light flashes. If the monkey moves its eyes toward the light, it receives a drop of fruit juice as a reward. By recording from dopamine neurons throughout training, Schultz could track how these neurons responded as the monkey learned the task. What he observed was completely unexpected. Initially, when the juice reward was unpredicted, the monkey had no idea it was coming. Dopamine neurons fired vigorously at the moment the juice was delivered. This made sense. The neurons seemed to be signaling reward received. But as training continued and the monkey learned that the light predicted juice, something remarkable happened. The dopamine response to the juice itself gradually diminished. It grew weaker. Eventually, it disappeared entirely. At the same time, a new response emerged. At the moment, the light appeared. The dopamine neurons that had been silent when the light first appeared now fired strongly. The response had transferred from the reward itself to the earliest predictor of the reward. And then Schultz did something brilliant. He occasionally omitted the juice reward. The light would flash, but no juice would follow. When this happened, dopamine neurons showed a dip in their firing, a depression below baseline, at the exact time the juice should have arrived. Schultz realized he was witnessing something profound. Dopamine neurons weren't simply responding to rewards. They were responding to the difference between predicted and actual rewards, to what computer scientists call prediction errors. When the outcome was better than predicted, dopamine neurons increased their firing. A positive prediction error. When the outcome matched predictions exactly, dopamine neurons stayed silent. No prediction error. When the outcome was worse than predicted, dopamine neurons decreased their firing below baseline. A negative prediction error. This pattern matched a computational algorithm developed independently in artificial intelligence research, temporal difference learning. In this framework, an agent learns to predict future rewards by iteratively adjusting predictions based on prediction errors. It's one of the most powerful learning algorithms in machine learning. And Schultz had discovered that dopamine neurons in the primate brain were implementing this exact algorithm. Let this sink in for a moment. Your brain doesn't signal, "this is good," in any absolute sense. It signals, "this is better than expected," or "this is worse than expected." It's encoding a relative signal, a comparison between prediction and reality. This completely reframes what dopamine does. Dopamine isn't reporting objective value, it's reporting the error in your value predictions. It's teaching your brain to update its models of the world. It's the mechanism by which experience shapes future expectations. This is why novelty feels inherently rewarding. Novel stimuli have uncertain predicted values, so actual outcomes are likely to differ from predictions, generating prediction errors. This is why surprising gifts feel more exciting than expected ones. This is why routine pleasures lose their motivational pull even though they remain objectively pleasant. When you can perfectly predict an outcome, there's no prediction error to signal, no dopamine burst to generate that feeling of excitement. The pleasure may remain, liking, but the anticipatory thrill is gone. Wanting. And here's where it connects back to addiction. Drugs create massive, artificial prediction errors. Dopamine surges far larger than anything natural rewards produce. These enormous positive prediction errors teach the brain that drug-related cues predict extraordinarily valuable outcomes. The associations form rapidly and powerfully. Over time, with repeated use, predictions adapt. The brain learns to expect these large dopamine surges. But here's the insidious part. Sensitization of cue-triggered dopamine release means that drug-related cues continue generating prediction errors, and dopamine release even as the drug itself becomes less rewarding. The cues predict more value than the drug actually delivers, but the cue-triggered wanting persists. This creates a vicious cycle. Cues trigger craving, wanting. Craving drives drug seeking. Drug use produces less pleasure than predicted, negative prediction error after consumption. But the cues continue triggering positive prediction errors, because the dopamine response to cues is sensitized, so the cycle repeats. The prediction error framework also suggests why relapse is so common in addiction. Even after long abstinence, the associations between drug cues and value predictions remain encoded in neural circuitry. When a recovering addict encounters drug-related cues, those cues can still trigger dopamine release and prediction errors, creating intense craving despite conscious intentions to stay sober. For his groundbreaking discovery about dopamine and prediction errors, Schultz received the Brain Prize in 2017, shared with Peter Dian and Ray Dolan, who contributed theoretical interpretations connecting the neural data to computational learning theory. But the implications extend far beyond addiction and learning. They fundamentally alter how we think about motivation, decision-making, and conscious experience itself. Part 5. The Architecture of Desire. To truly understand how dopamine shapes behavior, we need to explore the anatomy, the neural geography where these processes unfold. Picture your brain as a vast city, with dopamine neurons as messengers carrying signals along specific routes, connecting distant neighborhoods that need to coordinate their activities. The journey begins deep in the midbrain, in two small regions, the ventral tegmental area, VTA, and the substantia nigra pars compacta. Despite containing relatively few neurons, approximately 5,000 dopamine neurons in the VTA and roughly 400,000 in the substantia nigra, these populations wield extraordinary influence through their extensive projections. From the VTA, dopamine neurons send axons forward through two main highways, the mesolimbic pathway and the mesocortical pathway. The mesolimbic pathway projects to the nucleus accumbens, a structure sitting at the base of the forebrain that serves as a critical interface between motivation and action. The nucleus accumbens receives emotional input from the amygdala, contextual information from the hippocampus, and executive signals from the prefrontal cortex, integrating all this information to translate motivational states into motor behaviors. Within the nucleus accumbens, there are two main types of dopamine receptors that have opposing effects. D1-like receptors, D1 and D5, couple to stimulatory signaling pathways. When activated, they make neurons more likely to fire. D2-like receptors, D2, D3, and D4, couple to inhibitory pathways. When activated, they generally make neurons less likely to fire. The balance of activation across these receptor types creates the nuanced effects of dopamine. It's not simply on or off. It's a complex modulation that can amplify certain signals while suppressing others, depending on which neurons express which receptors and what other inputs they're receiving. The mesocortical pathway projects from the VTA to the prefrontal cortex, particularly regions involved in planning, decision-making, working memory, and cognitive control. This allows dopamine to influence not just immediate motivation, but also higher-order executive functions that plan for the future and inhibit inappropriate impulses. Meanwhile, the substantia nigra projects primarily to the dorsal striatum, the caudate nucleus and putamen, forming the nigrostriatal pathway. This pathway is critical for motor control and habit learning. The progressive death of these dopamine neurons is what causes Parkinson's disease. The striatum is organized into parallel loops that connect cortex, striatum, pallidum, thalamus, back to cortex. Different loops handle different types of information. Motor loops coordinate movement. Associative loops support goal-directed decisions. Limbic loops process emotional and motivational information. Dopamine modulates all these loops, adjusting how information flows through them based on prediction errors and motivational states. At the molecular level, dopamine's effects unfold through carefully orchestrated processes. Dopamine is synthesized from the amino acid tyrosine through a two-step process. Tyrosine hydroxylase converts tyrosine to L-dopa, then dopa decarboxylase converts L-dopa to dopamine. This happens in the cell bodies of dopamine neurons in the VTA and substantia nigra. The dopamine is then packaged into vesicles, tiny membrane-bound containers that store neurotransmitters until they're needed. When an action potential arrives at the axon terminal, voltage-gated calcium channels open. Calcium rushes in, triggering vesicles to fuse with the presynaptic membrane and release their dopamine cargo into the synaptic cleft. Dopamine molecules diffuse across this narrow gap and bind to receptors on postsynaptic neurons. Once bound, they trigger cascades of intracellular signaling through G proteins and second messengers like cyclic AMP, ultimately influencing gene expression and synaptic plasticity. The signal is terminated through reuptake, dopamine transporters on the presynaptic membrane pump dopamine back into the terminal for recycling or degradation. Enzymes like monoamine oxidase, MAO, and catechol O-methyltransferase, COMT, break down dopamine into inactive metabolites, ultimately producing homovanillic acid. This is where drugs of abuse intervene. Cocaine blocks dopamine transporters, preventing reuptake and causing dopamine to accumulate in the synapse. Amphetamine reverses the transporter, forcing dopamine out even without action potentials. These pharmacological manipulations create dopamine surges far exceeding anything natural rewards can produce. Understanding this architecture reveals why dopamine dysfunction has such diverse consequences. Lose dopamine in the nigrostriatal pathway. You get Parkinson's disease and motor problems. Excessive dopamine in mesolimbic circuits. Current evidence suggests possible contributions to psychotic symptoms in schizophrenia, though this remains an area of active research. Blunted dopamine responses to natural rewards, one mechanism that may contribute to depression and anhedonia. Sensitized dopamine responses to drug cues, a core feature of addiction. But the system's elegance also creates vulnerability. Evolution shaped dopamine circuits to respond to natural rewards that were scarce and unpredictable in ancestral environments. Food, mates, novel resources. These systems now operate in modern contexts radically different from those they evolved for, with engineered foods designed for maximum palatability, drugs that directly manipulate neurotransmitter levels, and technologies delivering unpredictable rewards on variable ratio schedules. The mismatch between evolved function and modern environment may explain much about contemporary behavioral health challenges. Part 6. What the brain learns to want. If dopamine teaches the brain what's worth pursuing through prediction errors, what naturally activates this system? What are the fundamental rewards that evolution wired us to seek? The answer begins with survival imperatives: food, water, sex, social bonding, behaviors essential for individual survival and reproduction. Species that didn't find these activities motivating went extinct. Natural selection shaped dopamine systems to make survival-relevant behaviors powerfully rewarding. Consider hunger. When you're food-deprived, dopamine neurons in the VTA become more responsive to food-related cues. The smell of cooking, the sight of a restaurant, even thoughts about eating can trigger dopamine release. This creates focused attention on food-related information and energizes food-seeking behavior. But food reward isn't simply about caloric intake. Sweet tastes trigger particularly strong responses because in ancestral environments, sweetness reliably predicted energy-dense calories, a valuable resource when food scarcity was common. Fatty, rich foods activate reward circuits because fats are calorie-dense and essential for various bodily functions. Salt is rewarding because sodium is necessary for cellular function and was relatively scarce in many evolutionary contexts. Interestingly, when you're sated, when hunger is satisfied, dopamine responses to food cues diminish substantially. The same food that would have generated strong prediction errors an hour ago now evokes much weaker responses. This demonstrates that dopamine signaling is modulated by internal state. The reward system doesn't respond to stimuli in a fixed way. It dynamically adjusts based on current needs and physiological conditions. Social rewards are equally fundamental to human motivation. Humans evolved in small cooperative groups where social bonds determined survival. Positive social interactions, conversation, laughter, signs of friendship, romantic connection, activate dopamine pathways. Brain imaging studies show that receiving positive social feedback, expressions of affection, or signals of increased status activate the nucleus accumbens and related reward regions. This social tuning of the reward system has profound implications. Much of human motivation is oriented toward social goals: status, reputation, fairness, belonging. We work hard for promotions partly for material benefits, but perhaps equally for social recognition. We avoid certain actions not just because of intrinsic costs, but because of potential social disapproval. The dopamine system, rather than being narrowly focused on selfish hedonism, appears to incorporate complex social valuations. Novelty itself functions as a reward, which initially seems puzzling. Why would mere novelty, independent of any specific benefit, activate reward pathways? The answer, researchers believe, lies in information value. In uncertain environments, exploration provides information about potential resources, threats, and opportunities. Novel stimuli represent unknowns, and investigating unknowns can lead to valuable discoveries. Evolution appears to have built systems that reward exploration, making novelty intrinsically motivating. This is why children spontaneously investigate their environments, why scientists pursue knowledge for its own sake, why travelers seek unfamiliar places. This exploratory drive is dopamine-mediated. Novel stimuli trigger dopamine responses that create curiosity and approach motivation. Learning and mastery can also be rewarding in themselves. When you suddenly understand something previously confusing, when you master a skill, when you solve a difficult puzzle, these moments of insight and competence activate reward circuits. From an evolutionary perspective, this makes adaptive sense. Organisms that find learning intrinsically rewarding will acquire knowledge and skills more readily than those that don't. Even physical exercise, despite being effortful and sometimes uncomfortable, can activate reward pathways. The phenomenon, sometimes called runner's high, appears to involve endorphin and endocannabinoid release, but changes in dopamine activity may also contribute. The reward system seems to encode the long-term value of physical fitness, creating positive associations with activities that promote it, even when those activities are acutely demanding. Music provides a fascinating example that stretches the boundaries of evolutionary explanation. Listening to music we enjoy activates the nucleus accumbens. Moments of particular beauty or emotional intensity, those chills, correlate with dopamine release. Yet music, at least in ancestral environments, provided no obvious survival advantage. There were no calories in a song. This suggests that the reward system can be co-opted by cultural innovations, by stimuli that engage pattern recognition, emotional processing, or social signaling in ways that trigger dopamine release despite not serving the system's original evolutionary purposes. Art, literature, humor, religious or spiritual experiences, many elements that enrich human life, may work partly by engaging reward circuitry in novel ways that evolution didn't specifically design, but that our flexible learning systems can incorporate. Even abstract goals, completing meaningful work, achieving fairness, helping others, pursuing truth, can activate dopamine pathways once they've been culturally and personally encoded as valuable. This remarkable flexibility allows the reward system to extend far beyond immediate biological needs, supporting the richness of human culture and motivation. But this same flexibility creates vulnerability. If the reward system can learn to value abstract cultural achievements, it can also learn to value empty rewards, stimuli that provide dopamine responses without promoting well-being. Part 7. The spectrum of human difference. One of the most fascinating aspects of dopamine function is its profound variability across individuals. No two people have identical dopamine systems, and these differences shape personality, decision-making, vulnerability to disorders, and the subjective texture of experience itself. At the genetic level, variations in dopamine-related genes create a spectrum of function. Consider the DRD2 gene, which encodes D2 dopamine receptors. A common genetic variation called the TAQ1A polymorphism comes in two main variants, A1 and A2. Individuals carrying the A1 allele have approximately 30% fewer D2 receptors in the striatum, compared to those with the A2 variant. This difference has behavioral consequences. With fewer receptors, baseline dopamine signaling is effectively reduced. Rewards may feel less satisfying. To compensate, individuals carrying the A1 allele may be more likely to engage in intense reward-seeking behaviors, including risk-taking, novelty-seeking, and substance use. The A1 allele is overrepresented in populations with alcoholism, drug addiction, and pathological gambling, suggesting this genetic variant may create vulnerability by altering how rewarding various experiences feel. Other genetic polymorphisms affect different aspects of dopamine function. The DAT1 gene encodes the dopamine transporter, the protein that pumps dopamine out of the synapse. Variants producing more efficient transporters result in faster dopamine clearance, effectively reducing the duration of dopamine signals. The COMT gene encodes catechol-O-methyltransferase, the enzyme that breaks down dopamine, particularly in the prefrontal cortex. The Val140-MET polymorphism affects enzyme activity. Val variants produce higher enzyme activity and faster dopamine degradation, lower prefrontal dopamine, while MET variants produce lower activity, higher prefrontal dopamine. These genetic differences correlate with cognitive trade-offs. Val carriers with lower prefrontal dopamine tend to show better cognitive stability, sustained focus on current tasks, but worse cognitive flexibility, difficulty shifting strategies when circumstances change. MET carriers show the opposite pattern. This illustrates how genetic variation creates trade-offs rather than simply better or worse variants. Personality traits correlate with dopamine function, extroversion, the tendency toward sociability, positive emotion, and behavioral approach, appears associated with higher dopaminergic tone. Extroverts show stronger responses to rewards, greater approach motivation, and more activity in reward-related brain regions during positive experiences. Research suggests that individuals high in behavioral activation or approach motivation are energized by reward cues, persistent in pursuing goals, and strongly affected by positive outcomes, but also potentially more vulnerable to addictive behaviors because their reward systems are highly responsive. Intelligence and creativity show complex relationships with dopamine function that researchers are still working to fully understand. Some evidence suggests an inverted U relationship, where optimal cognitive performance requires moderate dopamine levels. Too little produces apathy and sluggish thinking. Too much produces distractibility and disorganized thought. Creative thinking, in particular, may benefit from specific patterns of dopamine activity that enhance cognitive flexibility and the ability to make remote associations. Environmental factors interact with genetics throughout development. Early life experiences shape dopamine system maturation. Enriched environments, characterized by cognitive stimulation, social interaction, physical activity, and varied experiences, appear to promote healthy dopamine function. Conversely, chronic stress, neglect, and trauma can dysregulate dopamine signaling, altering receptor densities, baseline dopamine levels, and stress responsivity in ways that may persist into adulthood. Consider ADHD, a condition strongly linked to dopamine dysfunction. Genetic variants affecting dopamine function, particularly in prefrontal cortex and its connections to the striatum, create vulnerability. But whether this vulnerability manifests as full-blown ADHD depends substantially on environmental factors, prenatal exposures, early childhood stress, parenting approaches, educational support, and social environment. Gene-environment interactions determine outcomes. Cultural factors add yet another layer. Different cultures emphasize different values, which shapes what the reward system learns to find rewarding. In societies that prioritize individual achievement, personal accomplishments may strongly activate reward circuits. In collectivist cultures, social harmony and group success may generate more powerful dopamine responses. These culturally constructed rewards still operate through the same dopamine mechanisms, but they reflect learned associations between outcomes and value. Sex differences exist as well. Males and females differ, on average, in dopamine receptor densities, dopamine release patterns in response to various stimuli, and sensitivity to dopaminergic drugs. These differences may contribute to sex differences in rates of addiction, depression, ADHD, and other conditions. Hormones like estrogen and testosterone interact with dopamine systems, modulating receptor expression and neuron excitability. Across the menstrual cycle, women show fluctuations in dopamine function that affect mood, motivation, and drug sensitivity. Aging brings progressive changes. Dopamine synthesis declines, dopamine receptors decrease in number, and the responsiveness of dopamine neurons to rewards diminishes. These changes may contribute to reduced novelty-seeking and altered motivation in older adults, though wisdom and accumulated experience can provide alternative sources of meaning and engagement. The spectrum of individual differences highlights a crucial point. There's no single optimal dopamine configuration. Evolution maintains genetic diversity precisely because different variants prove advantageous in different contexts. A person with a reward system tuned for high novelty seeking might thrive as an entrepreneur or explorer, but struggle with addiction or impulsivity. A person with a more cautious reward system might avoid those pitfalls, but miss opportunities for discovery and achievement. Understanding these individual differences encourages moving beyond simplistic categorizations of disordered versus normal, instead appreciating the diversity of motivational profiles that exist across human populations. Part 8. When systems fail. Understanding how dopamine normally functions illuminates what goes wrong in various neurological and psychiatric conditions. These disorders reveal, through their pathology, the essential roles dopamine plays in movement, cognition, emotion, and motivated behavior. Parkinson's disease results from the progressive death of dopamine neurons in the substantia nigra, the population projecting to the dorsal striatum. As these neurons die over years to decades, dopamine levels in the striatum plummet. Motor symptoms emerge: bradykinesia, slowness of movement, rigidity, resting tremor, and postural instability. These occur because the basal ganglia, deprived of dopamine, can no longer properly regulate motor programs. But Parkinson's affects more than movement. Many patients develop depression, anxiety, and apathy, non-motor symptoms that likely reflect dopamine loss in mesolimbic and mesocortical pathways. Cognitive changes, particularly in executive function and working memory, also occur. Interestingly, some patients on dopamine replacement therapy develop impulsive behaviors, compulsive gambling, shopping, or hypersexuality, possibly because the medication overshoots normal levels in relatively preserved reward pathways while treating depleted motor pathways. L-DOPA remains the primary treatment. It crosses the blood-brain barrier, gets converted to dopamine, and temporarily restores dopamine levels, often producing dramatic symptom relief. But L-DOPA has limitations. It doesn't stop the underlying neurodegeneration. Over time, as more dopamine neurons die, effectiveness wanes and motor fluctuations emerge. Non-pharmacological approaches, deep brain stimulation, physical therapy, lifestyle modifications, complement medication. Attention deficit hyperactivity disorder, ADHD, is characterized by inattention, hyperactivity, and impulsivity. While ADHD's neurobiology is complex, dopamine dysfunction, particularly in prefrontal cortex and its striatal connections, plays a central role. Neuroimaging studies show altered dopamine transporter density, evidence suggesting blunted dopamine release in response to rewards, and reduced activity in prefrontal regions during tasks requiring sustained attention. The treatment paradox, using stimulants to calm hyperactive children, makes sense in this framework. The hyperactivity doesn't stem from excess dopamine, but from insufficient dopamine in circuits supporting attention and impulse control. Methylphenidate, Ritalin, and amphetamines, Adderall, increase dopamine signaling, improving prefrontal function. This enhances the ability to sustain attention, resist distractions, and inhibit inappropriate responses, often reducing hyperactive behavior by strengthening the underlying control mechanisms. Schizophrenia involves perhaps the most complex relationship with dopamine. The dopamine hypothesis, proposed in the 1960s, suggested excessive dopamine activity causes psychotic symptoms, based on observations that dopamine-increasing drugs can induce psychosis, and that antipsychotic medications all block dopamine receptors. Modern research suggests a more nuanced picture. Current evidence indicates that schizophrenia may involve excessive dopamine activity in subcortical regions like the striatum, which researchers believe could contribute to positive symptoms like hallucinations and delusions, while simultaneously involving insufficient dopamine in prefrontal cortex, potentially contributing to negative symptoms, flat affect, social withdrawal, and cognitive deficits. This dysregulation model proposes imbalanced dopamine across different brain regions rather than simple excess, though the precise mechanisms remain an active area of investigation. Antipsychotic medications, by blocking D2 receptors, can reduce positive symptoms in many patients. However, they're generally less effective for negative symptoms and cognitive deficits, and they often cause troubling side effects, weight gain, metabolic problems, and movement disorders. The challenge is that globally blocking dopamine receptors affects all dopamine pathways, potentially improving psychosis while impairing motivation, cognition, and motor function. Depression, particularly subtypes characterized by anhedonia and lack of motivation, appears to implicate dopamine dysfunction among other neurobiological factors. While serotonin has received more attention, accumulating evidence suggests dopamine also plays an important role. Research shows that depressed individuals often display blunted responses to rewards, reduced motivation, and decreased activity in reward-related brain regions in functional imaging studies. Some antidepressants target dopamine. Bupropion, Wellbutrin, a norepinephrine dopamine reuptake inhibitor, appears particularly effective for depression characterized by low energy, poor motivation, and anhedonia. This suggests that depression isn't a monolithic entity, but rather encompasses different subtypes with different neurobiological underpinnings. Obsessive-compulsive disorder, OCD, Tourette syndrome, bipolar disorder, autism spectrum disorder, and other conditions also show evidence of dopamine system abnormalities, though the precise mechanisms remain active areas of research. What becomes clear is that dopamine dysfunction manifests differently depending on which circuits are affected, which receptor types are involved, and how dopamine interacts with other neurotransmitter systems. The future of treating dopamine-related disorders likely involves greater precision, medications targeting specific receptor subtypes, circuit-specific interventions using techniques like deep brain stimulation, and personalized approaches based on individual genetic and neurobiological profiles. We're not there yet, but progress continues. Part 9. Living in a dopamine world. As we step back to consider the full picture, certain patterns emerge. Dopamine isn't about pleasure or happiness in any simple sense. It's about learning what matters, building an internal model of the world's reward structure, and using that model to guide behavior. It operates through prediction errors, signaling when reality exceeds or falls short of expectations. It creates wanting, not liking, motivation to pursue rewards rather than the pleasure of consuming them. It shapes which cues grab our attention, which goals feel worth pursuing, which actions seem worth taking. This system evolved for survival in ancestral environments where rewards were scarce and unpredictable. But now it operates in modern contexts radically different from its evolutionary origins. Engineered foods deliver supernormal combinations of sugar, fat, and salt that activate reward circuits far more intensely than anything available to our ancestors. Drugs directly manipulate dopamine levels, creating artificial prediction errors that hijack learning systems. Technologies deliver unpredictable rewards, notifications, likes, wins, on variable ratio schedules known to be maximally reinforcing. The mismatch between evolved function and modern environment creates both opportunities and vulnerabilities. Understanding this mismatch provides perspective on contemporary behavioral health challenges. But understanding also empowers choice, not unlimited choice, but informed choice within constraints. We can structure our environments to promote healthy dopamine function, prioritizing adequate sleep, engaging in regular exercise, cultivating meaningful social connections, pursuing intrinsically motivated goals, being mindful of how modern technologies exploit dopamine mechanisms. We can approach addiction with compassion rather than moral judgment, recognizing it as a learning system that has been hijacked rather than a character flaw. We can understand that anhedonia in depression reflects disrupted prediction error signaling, not laziness. We can appreciate that personality differences partly reflect dopaminergic variation and celebrate diversity rather than pathologizing difference. The science also raises profound questions. What does it mean to want something? Is motivation the same as free will? If desires reflect dopamine signals shaped by neural circuitry and past learning, are they truly ours? These philosophical questions don't have simple empirical answers, but neuroscience informs them, showing that motivation emerges from complex dynamical systems combining top-down control with bottom-up drives, conscious deliberation with non-conscious impulses. Perhaps most fundamentally, understanding dopamine reminds us that we are biological beings, evolved organisms whose brains reflect solutions that natural selection discovered to ancient problems. The dopamine system is one such solution, an elegant mechanism for learning what's rewarding and motivating pursuit. But like all evolved systems, It sometimes misfits present circumstances. Our challenge is living with these evolved brains in modern contexts they weren't designed for, finding ways to promote well-being despite, and sometimes because of, this mismatch. Part 10. The Revelation. As we reach the end of this journey, let's return to where we began, to that heroin addict, trembling hands reaching for something they hate. Now you understand the mechanism. You know about wanting versus liking. You know about prediction errors and sensitization. You understand how dopamine creates motivation separate from pleasure, how cues can trigger craving through processes that bypass conscious control. But here's what you might have missed. Here's the revelation that changes everything. This wanting-liking dissociation, this apparent malfunction that creates addiction, isn't a malfunction at all. It's the design. Think carefully about what would happen if wanting and liking were perfectly coupled, if you only wanted things in exact proportion to how much pleasure they'd bring in that moment. You'd never pursue difficult long-term goals. The immediate discomfort would always outweigh the distant reward. You'd never learn challenging skills. The frustration of practice would eliminate motivation before mastery arrived. You'd never make sacrifices for future benefit. You'd never delay gratification. You'd never endure present pain for greater future gain. You'd be trapped in the immediate present, unable to act for tomorrow. The ability for wanting to exceed immediate pleasure is precisely what allows humans to pursue multi-year education, build civilizations, create art that takes decades to master, sacrifice for children's futures, and work toward abstract goals that may never provide simple hedonic rewards. The separation of wanting from liking is what makes human achievement possible. And the prediction error mechanism? That's not a bug either. If dopamine only signaled absolute value, if it just told you, this is good, or this is bad, you'd be stuck pursuing whatever gave you the strongest initial reward, unable to adapt when circumstances changed, unable to discover better alternatives. But by signaling prediction errors, deviations from expectations, the system solves the explore-exploit dilemma that every learning system faces. When predictions are uncertain, outcomes generate strong prediction errors that motivate exploration. When predictions are accurate, the lack of prediction errors promotes exploitation of known rewards. You explore when you should explore. You exploit when you should exploit. All without conscious deliberation. And sensitization? The process that makes addiction so persistent? That same mechanism allows you to become passionate about pursuits that initially weren't rewarding, to develop deep interests, to find meaning in challenging work, to build motivation for activities that require sustained effort before they become enjoyable. Every mechanism we've discussed, wanting separate from liking, prediction error learning, sensitization to cues, the transfer of dopamine responses from outcomes to predictors, serves essential adaptive functions in normal life. But evolution couldn't anticipate cocaine. It couldn't predict that humans would discover how to synthetically create massive dopamine surges that dwarf anything natural selection prepared the brain to handle. It couldn't foresee that we'd engineer foods combining sugar, fat, and salt in combinations that never existed in nature. It couldn't imagine technologies delivering unpredictable social rewards on schedules optimized to maximize engagement. The same system that enables your greatest achievements can be hijacked to create your deepest suffering. This is the paradox at the heart of the human condition. The neural machinery that makes us capable of remarkable things, of art, science, love, sacrifice, and meaning, is the exact same machinery that makes us vulnerable to addiction, compulsion, and desire detached from well-being. We don't have two dopamine systems, one for good pursuits and one for harmful ones. We have one system, and whether it drives us toward flourishing or suffering depends on what activates it, what patterns it learns, what environment it develops within. When you understand this, truly understand it, everything shifts. Addiction stops being a moral failure and becomes a learning system exposed to input it wasn't designed to handle. The addict wanting what they hate isn't weak. They're experiencing the normal operation of a wanting system that has been sensitized to cues predicting a reward. Their brain's prediction error system says is extraordinarily valuable, even though the liking system knows it's not. Depression's anhedonia isn't laziness, it's a prediction error system that has stopped signaling opportunities, stopped marking goals as worth pursuing, stopped generating the wanting that makes action feel possible. And your own struggles, the difficulty resisting that phone notification, the challenge of maintaining motivation for long-term goals, the disappointment when achievements feel hollow, all make sense as features of a system that's doing exactly what it evolved to do, just in circumstances wildly different from its evolutionary context. Understanding doesn't grant unlimited control. The dopamine system operates largely outside conscious awareness. You didn't choose your genetic variants. You don't directly control receptor densities or enzyme activities. You can't simply decide to have different prediction errors. But understanding grants something equally valuable: perspective, compassion, and the possibility of informed choice within constraints. You can structure your environment to promote healthy dopamine function. You can be mindful of how technologies exploit these mechanisms. You can recognize when wanting has decoupled from well-being and make conscious choices to override automatic impulses. You can approach others' struggles with compassion rather than judgment, knowing that addiction, depression, and compulsion reflect neural mechanisms we all share, just pushed to extremes. The revelation isn't that dopamine is good or bad, it's that dopamine is powerful, a learning system of extraordinary sophistication that makes us capable of both the sublime and the tragic. And now, when you see that addict reaching for what they hate, you understand. You see the prediction errors firing. You see the wanting divorced from liking. You see the sensitized cue responses. You see a learning system doing exactly what it's designed to do: pursue predicted value marked by dopamine, independent of pleasure. You see not moral weakness, but neural architecture. Not choice, but mechanism. Not failure, but the inevitable consequence of powerful systems meeting inputs they weren't shaped to handle. And perhaps, in that understanding, you find both humility, recognizing how much of motivation operates beyond conscious control, and empowerment, seeing opportunities to work with these systems rather than against them, to structure environments and make choices that align automatic processes with conscious values. The dopamine system will continue its work tomorrow. It will mark significance, generate wanting, drive learning, shape your sense of what matters. Understanding it doesn't eliminate its power, but it transforms how you relate to your own desires, your own struggles, and the desires and struggles of others. That transformation, from seeing motivation as pure will to seeing it as neural mechanism, from judgment to compassion, from helplessness to informed choice, might be the most valuable insight neuroscience offers. The wanting-liking paradox we opened with isn't just about addiction. It's about being human. It's about having a brain shaped by evolution operating in a world evolution couldn't anticipate. It's about the price we pay for the same mechanisms that make us capable of everything we value most. That's the revelation. That's the truth hiding beneath the surface of every desire, every craving, every moment of motivated behavior. That's dopamine. That's us. And now you know. Rest well tonight. Let your mind wander back through this journey if it wants to. You might find yourself seeing earlier parts differently now, the paralyzed rabbits in Sweden taking on new meaning, the rats pressing levers revealing something deeper, Berridge's dopamine-depleted rats illustrating a principle that explains not just addiction, but human striving itself. This is one of those understandings that grows richer with reflection. The more you sit with it, the more you see its implications everywhere, in your own behavior, in others' struggles, in the design of the world around you. Tomorrow, when you notice yourself wanting something, pause for just a moment. Ask, is this wanting or liking? Am I pursuing this because I genuinely expect it to bring well-being, or because a sensitized circuit is generating motivation toward something that once did, or that prediction errors suggest should, even if the reality would disappoint? Those moments of awareness won't give you perfect control, but they offer something precious, the ability to work with your dopamine system rather than being unconsciously driven by it. Sleep gently with this knowledge. And if you found value in this exploration, consider continuing to learn about the intricate, beautiful, sometimes troubling mechanisms that make us who we are. The brain has many stories yet to tell, and each one illuminates another corner of the human experience. Until next time, rest in the understanding that you are a biological being with a chemical system of extraordinary sophistication, capable of both profound suffering and remarkable achievement, often through the very same mechanisms. You are dopamine in action. And now you know what that means. Good night.